So preparation of acid chlorides. Okay, organic chemistry 2. Today we're going to start with talking about acid chlorides, and the way we're going to start with acid chlorides is just talking about how to make an acid chloride. Just to refresh your memory, this entire chapter is about carboxylic acids and their derivatives, and I think that everybody here knows what a carboxylic acid is, and that we call this group a carboxyl group. So carboxylic acid, but if you replace the hydroxyl of a carboxylic acid with a chlorine, you get an acid chloride. And acid chlorides are really reactive. They're more reactive than anhydrides. They're more reactive than esters and amides. And we said the reason why an acid chloride is so reactive is because it's got a super electrophilic carbon. You've got a dipole pulling this way and pulling this way on this carbon, which renders it very electrophilic. And so it's very susceptible to nucleophilic attack. Now that's a little bit of what we covered last class, but today we're going to start with how would you make an acid chloride? If you wanted to make an acid chloride, what would you do? Well, making an acid chloride is in fact a very straightforward reaction. I hesitate to use the word simple in organic chemistry, but I'd say it's a pretty straightforward reaction. What you do is you take the carboxylic acid and you combine it with SOCl2, which is called thionyl, so thionyl chloride. Thionyl chloride. And if we draw the Lewis structure of thionyl chloride, it looks something like this. There we go. So thionyl chloride like that. So there's our thionyl chloride. And thionyl chloride reacts with the hydroxyl group of our carboxyl group. It reacts with the carboxylic acid, I should say, to make an acid chloride. So here's our acid chloride. And what's cool about this reaction is that you make sulfur dioxide, and sulfur dioxide is a gas. Okay? Anytime you have a reaction where you liberate a gas, that gas is going to go up into the atmosphere, and that's going to render this reaction irreversible, right? The gas isn't coming back. So this is a very good reaction to get a beginner to do in the lab. All they have to do is mix a carboxylic acid and some thionyl chloride, which is a liquid at room temperature. You just drop it in, and as soon as you see the bubbles subside, you know the reaction is over. Of course, you would check it with a TLC or something. But there you go. That's how you make an acid chloride, just with some thionyl chloride. But the acid chloride, like I said, is very electrophilic. And so if you put it in water, it's going to react extremely quickly, just bang, like a gunshot. And I talked about that a little bit last class, to regenerate the carboxylic acid. And you produce hydrochloric acid, which we know is a strong acid. So you make HCl and you liberate the carboxylic acid. But since HCl is a byproduct of hydrolysis, sometimes and oftentimes we'll put pyridine in the reaction mixture to neutralize that HCl. If we combine pyridine, which is a base, with HCl, which is an acid, the pyridine is going to take the proton to make pyridinium chloride. So we end up consuming that strong acid. And if you're wondering, well, why would you want to consume the strong acid? What's the big deal? Well, oftentimes organic chemists will do reactions where they will have another functional group in a molecule maybe that might be sensitive to a strong acid. And so having a strong acid around is not a good thing. Now, one funny thing that I'll just mention about this reaction before we go to the next page, and this is something I would never quiz you on, but it's just kind of an interesting aside, is that in this chapter, there's a couple of reactions that he teaches in the book, and it literally says in the text, now that you've learned this reaction, it's not very useful. And in fact, this reaction, I'll put here, has little synthetic utility. Synthetic utility. And the reason why is because normally acid chlorides are made from a carboxylic acid. So why the heck would you want to take it and blow it apart? There's really not a lot of use for that. But the rationale still stands that a student should understand that an acid chloride is going to react with water to produce a carboxylic acid. So let's take a look at this synthetic utility of acid chlorides in more detail. What if we have an alcohol? So here's a primary alcohol, and we're reacting it with some kind of acid chloride, and we have pyridine to, of course, mop up that HCl. What do we get? We end up making an ester. Okay, and now we're looking at it from the point of view of, okay, we're kind of treating the alcohol like the substrate. This is our reagent, you know, the acid chloride and the pyridine, and we end up making the ester. Well, what's cool about this is that you can do selective acylations, right? We call this an acylation reaction because this is an acyl group here. So this is an acyl group. So we call it an acylation. We say this is acylated. In this molecule, you've got two kinds of alcohols, don't you? You've got a secondary alcohol and a primary alcohol. Well, which one is less sterically hindered? The primary alcohol is much less sterically hindered. And so if you put one equivalent of an acid chloride, and this is called acetyl chloride because it's got two carbons. So this would be acetyl or acetyl, but this is acetyl chloride. Chloride, like acetyl coenzyme A. Anyhow, so acetyl chloride is going to react with the primary alcohol selectively because it's less sterically hindered, and you leave the secondary alcohol open, which is kind of interesting. All right, so now that we've learned how to make an acid chloride, and we've learned the reaction of an acid chloride with water, the reaction of an acid chloride with an alcohol, what else can you do with an acid chloride? We've talked about how to make an ester. We talked about how to blow it apart and regenerate the carboxylic acid. I said that's not very useful. But acid chlorides can be also used to make amides. And hopefully you remember that I went over this with you, I think once before, where we talked about amides, and I explained the difference between a primary amide. So this would be a primary amide where your nitrogen has two hydrogens. Then we have a secondary amide, that's where the nitrogen has one R group, and a tertiary amide is where the nitrogen has two R groups. So you need to know the difference between a primary, secondary, and tertiary amide. And we can synthesize a primary amide by taking an acid chloride and treating it with ammonia. Now notice that we have to use two equivalents of ammonia. So what does that mean, equivalents? It means that if you had 1 mole of this, you would need 2 moles of ammonia. Okay, so you need twice as much. Now, if you're wondering, well, why is that? Well, the reason you need twice as much of the ammonia, which is a base, okay, you need twice as much because, remember, you end up making HCl, and the second equivalent of the base acts just like a pyridine, and it neutralizes that HCl. So if you want to make a secondary amide, then you would use a primary amine. So this is a primary amine. Okay, so it's got 2 hydrogens on it. 2 equivalents, the same thing. And if you use a secondary amine, you end up with a tertiary amide. But again, we're not using pyridine to mop up the HCl. Now we're using the second equivalent of the amine, whether it's ammonia, a primary amine, or a secondary amine, to mop up that HCl. Now, one thing I'll say about this before we move on to talking about reduction of acid chlorides is that think about this. If you need 2 equivalents of your amine, okay, and it doesn't really count for ammonia because ammonia is cheap. But let's say the primary or secondary amine was something that you made. You actually went into the lab and said, I need this very customized primary or secondary amine. Well, what's crappy about this reaction, and it's kind of something you just have to deal with when you're a chemist, is the first equivalent goes into the molecule that you want, your amide, but the second equivalent, right, half of your starting material, half of that amine just goes in the waste. Okay, it's just used to neutralize the HCl and it's gone. Or, it's just nowhere. Okay, it goes in the trash. So, it's one of those reactions where sometimes you're like literally like wiping away a tear while you start the reaction. Like, well, there goes half of my hard work. All right, but as a chemist, that's what you're doing anyway. Anyhow, something kind of funny there. All right, let's talk about reduction of an acid chloride. So we've covered hydrolysis to make a carboxylic acid. We talked about making an ester. Now we've talked about making a primary, secondary, or tertiary amide. Now we're going to get into reducing an acid chloride. And this is a mechanism that I would expect you to know. I'm going to put a little star by mechanisms that I expect you to know. And this is, if you understood lithium aluminum hydride reduction that we looked at before, this one isn't much of a stretch, believe me. Okay, so we can reduce an acid chloride to a primary alcohol using lithium aluminum hydride. It's a two-step process. First step, take that acid chloride, treat it with lithium aluminum hydride. Think about it. Lithium aluminum hydride is a hydride delivery agent, right? It's an aluminum with a negative charge on it. And so it is able to deliver hydride, right? So what happens in the first step is, you can imagine the hydride is going to attack that electrophilic center. And that's what's drawn right here. I just redrew it. So we get that nucleophilic attack and we form a tetrahedral intermediate. We have three possible leaving groups. We could lose the R, the hydrogen, or the chloride. Well, chloride is the conjugate base of a strong acid, so it's what's going to scram. Then we end up with an aldehyde, and we looked at the reduction of an aldehyde way back in the alcohols chapter, because after it accepts a second hydride, it says second nucleophilic attack, we end up with an alkoxide, which gets protonated by water or acid. You can see that it says water here, but down here they drew hydronium. So we could put here water or H3O plus would be acceptable. And you end up with a secondary alcohol. So that's the mechanism. Again, not much of a stretch from what we looked at before when we talked about lithium aluminum hydride reduction. What's interesting is that you produce an aldehyde as an intermediate. All right, so you end up making an aldehyde, and then the aldehyde just gets reduced. All right, so there's another reaction. Well, if you're wondering, hey, Mr. Dion, would there be a way to stop here? Could I stop at the aldehyde? Well, unfortunately, with lithium aluminum hydride, you cannot do that. Okay, lithium aluminum hydride is a strong reducer. It's going to react with an aldehyde like nobody's business. But we can stop at the aldehyde. You can imagine chemists love to investigate ways to stop reactions and start reactions. So here we go. It says you can stop the reduction at the aldehyde. However, you got to learn a new reagent to do that. And the reagent that we use is, check it out. Check this name out. It's lithium tri-T-butoxy aluminum hydride. Whoa, that is a long name, isn't it? That one, lithium tri-T-butoxy aluminum hydride. But instead of writing that entire thing out, we write it out as I have shown here on the slide. We just write lithium aluminum, and then we put, instead of writing OB, like this, like for tert-butyl, we just write OR3 hydride. And here's the Lewis structure of it down here. Now, what happens is when you put these tert-butoxy groups on the aluminum, all it does, and I'm not going to give you some kind of full treatment about this because the book doesn't, but the idea is that it mitigates the reactivity of the hydride. Obviously, there's only one, okay? There's only one hydride in there anyway to deliver, but it mitigates the reactivity so it stops at the aldehyde, okay? It just tells you right here. It says lithium tri-T-butoxy aluminum hydride is more selective, reacts with acid chlorides faster than aldehydes, so the aldehyde can be isolated, okay? So even if you make some of the aldehyde in the reaction, if you have more of this in there before it's reacted with the acid chloride, it will still react with the acid chloride. It won't go for the aldehyde, okay? It's going to reduce it selectively. And again, this is one of those reactions that the mechanism isn't even put forth in the book. So there's no mechanism to know here. We can pencil that in here. So no mechanism. But you know what? I would guess that my students would be able to figure one out, or at least propose one, that you get a nucleophilic attack like this, you lose the chloride, you gain a proton, there you go, aldehyde, just like that. All right, so let's move on from there, and let's talk about the reaction of a Grignard with an acid chloride. And this is analogous to the Grignard reaction with an ester. Okay, so we'll put here like a Grignard with an ester. So this is something we would have seen in chapter 12. And again, not the exact same reaction, but it's similar to it. Check it out. We take our acid chloride, we react with excess Grignard, and the Grignard adds twice to the acid chloride. And then in the last step, you can treat it with water or H3O plus to protonate and make the alcohol. Now it says that the mechanism is analogous to the lithium aluminum hydride reduction, and it is. First step, we get the nucleophilic attack by our Grignard, lose the chloride because it's the best leaving group. Then we make a ketone. So we have a ketone formed along the way. And then we know that a ketone is definitely susceptible to nucleophilic attack by a Grignard. Absolutely it is. So then you make a tetrahedral intermediate, which gets protonated by your acid or water, and we end up with a tertiary alcohol. So we make tertiary alcohol. Okay, so what did we see with the lithium aluminum hydride? With the acid chloride, we took lithium aluminum hydride and we reduced it all the way down to a primary alcohol. Then I said, okay, well, if you take a weaker reducer like this lithium tri-T-butoxy aluminum hydride, you could reduce it just and stop at the aldehyde. And so now what we're going to see is that there is a way to stop at the ketone. Not using a Grignard reagent, it's using a brand new reagent. There's no mechanism. I'll put a blue star or a star by this one. This one I think is an important mechanism for my students to know. But there is no mechanism for this shown in the book. Okay, so no mechanism. Mechanism. There we go. No mechanism for this reaction. The Gilman reagent, lithium dialkyl cuprate, can be used instead of a Grignard. Another G, you got Grignard and Gilman. So Gilman reagents are what we call a dialkyl cuprate, a lithium dialkyl cuprate. So we have our copper and it's complex to two R groups. It's got a negative charge, and then you have the lithium cation to balance that out. Again, no mechanism to speak of in our textbook. And if you're the kind of person who has an inquiring mind and you want to look that up, no problem. You could maybe learn something about that. But I would say the mechanism would be beyond the scope of our course. Now, instead of writing it out like this all the time, normally the way that we write out the Gilman reagent would be like this. We just put R2, since there's two R groups, Cu, Li. Okay, that's how we write it like it is here. So let's say you had a methyl Gilman reagent. So you have two methyl groups, the copper and the lithium. We stop at the ketone. The methyl group adds, and then it's over. That's the end of the reaction right there. So now let's take a look. We've learned a lot in about 20 minutes of time. Now let's look at a summary of it all. Okay, let's look at a summary. First thing that we saw today, I think, was the formation of an acid chloride from the carboxylic acid. How did we do that? We used thionyl chloride. Then we said, if you take an acid chloride and put it in water, then it's going to make the carboxylic acid, which isn't really useful, but it's showing you how reactive the molecule is. And the pyridine is to mop up the HCl. And when I say mop up, it just makes it, it's just the organic chemistry speak, which means, neutralize it is all it is. Then we said, okay, well, if you react an acid chloride with an alcohol in pyridine, you can make an ester, right? And again, we need that pyridine to neutralize the HCl that's produced. Then we said, okay, if you take your acid chloride, you treat it with excess ammonia, you get a primary amide. If you treat it with excess of a primary amine, you get a secondary amide. If you treat it with excess of a secondary amine, you get a tertiary amide. The mechanism of that isn't even written. There's no mechanism for any of these in our textbook. However, if you look at the textbook, he even asks you the question in the text. It says, could you write a mechanism? I'm not going to ask you to write a mechanism, but it might be worth trying it out to see if you can write one. I know you can, okay? Anyhow, after that, we looked at lithium aluminum hydride reduction, followed by treatment with water or H3O plus, and that gives you a primary alcohol. And then we said you could actually stop at the aldehyde intermediate using lithium tri-T-butoxy aluminum hydride, followed by water or aqueous acid. That would work to stop at the aldehyde. Then this is a reaction that we saw in chapter 12, just as a reminder, where we treat, except we saw it with an ester, but anyhow, something similar, I'll say. We take our acid chloride, treat it with excess Grignard, followed by treatment with water or acid, and we end up making a tertiary alcohol, but we said we can stop at the ketone using a Gilman reagent. So this is the Gilman reagent, okay? Any kind of organocuprate with a lithium cation. Now that is a lot of chemistry. Now, we're going to take a look at some practice problems now, but one thing I just want to show you, these are the practice problems. We're going to look at acid chlorides in just a second, and I just want to skip ahead. And we see a pile of similarities between the reactions with acid anhydrides and acid chlorides. There's no such thing as an acid and chloride. I made that up. I'm kidding. But anyhow, so I just want to encourage you with that. If you understood the chemistry that we went over today, you're going to follow me on the chemistry of acid anhydrides, which we're going to look at next. All right, so let's get a little bit of practice. No mechanisms here. It just asks you to predict the major product for each of these reactions. All of them are acid chlorides. The first one is treating the molecule with excess lithium aluminum hydride, followed by water, and I'll put here or H3O+. I've mentioned this to you before, but I'll just put the bug in your ear again in case you're wondering, Mr. Dion, why do your slides always say H2O and then you add or H3O+? It's because he changed a couple things in the textbook. You know, every edition of the textbook changes it just enough to annoy professors and students alike, right? And I think that he was getting some heat from other scientists in the community saying, well, water can work, but there's a lot of scenarios where you can use aqueous acid. So basically, both of them are fine. It just depends on the situation, okay? All right, so let's see here. We got an acid chloride, excess lithium aluminum hydride. Let's go over here, and we see that we reduce the acid chloride to a primary alcohol. So let's draw the primary alcohol. Let's count our carbons very carefully. We have a total of 1, 2, 3, 4, 5 carbons. So let's pencil those in like this. And the carbon that I have numbered 1 is going to be converted into a primary alcohol. And there you have it, folks. So there's our primary alcohol. The next one, we have an acid chloride being treated with excess phenylmagnesium bromide. Could anybody tell me what kind of alcohol I'm going to get from this reaction? Would it be primary, secondary, or tertiary for this one? I'll just throw it out there to my students. If you have to go back and look, do it. Anybody have an idea about this one? Absolutely, yes. We get a tertiary alcohol, don't we? Why? It's because that Grignard adds twice. It adds once, you end up with a ketone in the reaction mixture, and the ketone undergoes a second addition. So that's this reaction right here, Sandrina, right? Here, we make a tertiary alcohol. So let's draw the tertiary alcohol. And let's count our carbons very carefully. It's the same substrate as the first reaction, isn't it? So now we're going to have, these are the carbons from our initial substrate. We have our alcohol, and now we've got two phenyl groups, one here and one here. So again, the first one, we get a primary alcohol, and now we've got a tertiary alcohol. Ooh, the next one is kind of interesting, isn't it? Because we have first the treatment of the acid chloride with lithium tri-T-butoxy aluminum hydride. And what that's going to do is that's going to convert the acid chloride to an aldehyde. I'm going to write that out first. So after the first step, we stop at the aldehyde like this. But then what it's saying is after that, you're treating it with a Grignard reagent followed by treatment with water or aqueous acid. And so if we take an aldehyde and we treat it with ethyl magnesium bromide, I'm kind of running out of space here, but the ethyl magnesium bromide is going to do a nucleophilic attack like this. And then after the proton transfer, so I'll just put H plus here, we're going to end up with this secondary alcohol. So we have our hydroxyl here, and then we have our 1, 2 carbons from our ethyl group. So we end up with secondary alcohol in this case. A lot of alcohol, a lot of alcohol synthesis here, huh? With the acid chlorides. All righty. Any questions about those three? Anything at all? All right. Give me a thumbs up if you follow me on. Is everybody with me on these ones? Even if you're like, you know what, Mr. Dean, I'm gonna have to study it. You know, give me a break. You know, I can't learn this in 20 minutes, which would be impossible. Okay, nobody could do that. Unless it's Goodwill Hunting or somebody, and even that was a made-up story, okay? So let's move on from there. Who wants to talk about some acid anhydrides? Tell you what, we'll do acid anhydrides, then we'll take a little breather, you know, to kind of catch our breath. Good news is, acid anhydrides, very similar to the chemistry of acid chlorides. So, first reaction, and this is a real classic in organic chemistry, is learning how to synthesize acetic anhydride. The way that this molecule is synthesized is just by taking acetic acid and beating the heck out of it, really. I mean, 800 degrees Celsius, that is extremely hot for a reaction in organic chemistry. When was the last time in our textbook that you ever saw 800 degrees Celsius? I think the answer is never. We usually talk about 50 degrees Celsius, 80 degrees Celsius, 100, you know, maybe, but not 800. I mean, that's extremely hot, and we can end up making acetic anhydride. The shorthand that chemists like to use, since an acetyl group is this, right? Just a carbonyl with a carbon on it. So the shorthand that we use for acetic anhydride is this, AC subscript 2, because there's 2 acetyl groups, and then O. That's the shorthand we use for acetic anhydride. Now check this out. It says that this reaction only works for acetic acid to make acetic anhydride. If you try it with any other carboxylic acid, it just ends up ruining it. So you're probably asking me, this is a very specific reaction. Why are you teaching me this? There's a good reason. It's because acetic anhydride is used as a reagent a lot in organic chemistry, and we're going to see several instances in the remainder of this class, maybe not today, maybe a couple times today, where we use acetic anhydride as a reagent. It's a very commonly used reagent for a variety of reasons in organic chemistry. So that's why we go over its synthesis. Now, what's the major difference between an acid chloride and an acid anhydride? Check it out. Look, if you look at an acid chloride, its leaving group is a chloride, which is the conjugate base of HCl, which is a strong acid. Whereas if we look at an acid anhydride, okay, so we'll just make acetic anhydride, its leaving group is the acetate ion, okay, or a carboxylate, which is the conjugate base of acetic acid, and acetic acid is a carboxylic acid. It's a weak acid. It's still a leaving group, but it's not as good a leaving group as chloride, the acetate, okay? And again, it's the conjugate base of a weaker acid. So I want you to have that in mind as we take a look at some of the reactions of acid anhydrides. Besides the synthesis of acetic anhydride, which is really only useful for making acetic anhydride, if you want to make an anhydride, here's a more practical way to make any other anhydride. What you do is you start out with an acid chloride and you treat it with a carboxylate. Okay, so again, this is called a carboxylate, right? 8 in chemistry. 8 means negative charge. Sulfate, nitrate, right? Carboxylate. So the nucleophile comes in and attacks, well, that's not a very good curved arrow, comes in and attacks our electrophile. That's this step right here. We form a tetrahedral intermediate. We lose chloride, which is the best leaving group, and we end up making our anhydride. So let's just say you did want to make an anhydride. That would be the preferred way to make it would be to take your acid chloride and treat it with the conjugate base of another carboxylic acid or a carboxyl. Okay, so now that we've got that settled, let's take a look at those two leaving groups. Now, I just went over this with you a couple of seconds ago, but they're both quality leaving groups. The chloride ion is a, oops, where's my black pen? Here it is. The chloride ion is a good leaving group, no doubt about that. And acetate, or a carboxylate, I should say, a carboxylate is also a good leaving group. It describes them as quality leaving groups. But we don't need to use pyridine with an anhydride. Why? Because we don't make a strong acid as a byproduct. Remember, when you protonate this, if this grabs a proton, you end up with HCl. That's a strong acid. If you protonate this, you end up with a carboxylic acid, which is a weak acid. And so pyridine is not required when we look at reactions using acid anhydrides. All right, gotta catch my breath here. So here is a kind of a review of the reactions of acid anhydrides and how they compare to acid chloride. So let's take a look. First thing we said was, if you take acetic acid and you crank it up to 800 degrees Celsius, you can make acetic anhydride, this specific compound. But we said, if you have another kind of carboxylic acid, a more practical method is to deprotonate first and then react it with some acid chloride, okay? So here they have acetyl chloride, and then you would end up with this compound. Okay, so that's the two ways that we learned to make an anhydride. We also said if you take acetic anhydride and you put it in water, it's just going to hydrolyze the whole dang thing, okay? Just blows it all apart. So acetic anhydride is labile or susceptible to hydrolysis in water. Next, we take our acid anhydride and we treat it with an alcohol and we end up making an ester. Again, notice, no pyridine required. You could even pencil that in here. No pyridine required. Why? Because when you do the proton transfer in the last step of the mechanism, you end up making a carboxylic acid, which is a weak acid, as opposed to HCl, which is a strong acid. After that, look at these reactions. I'm going to use my green highlighter. The synthesis of a primary, secondary, and tertiary amide are all exactly analogous to the ones where we synthesize those amides from an acid chloride. Next, the reaction with lithium aluminum hydride is exactly analogous. The one with lithium tri-T-butoxy aluminum hydride to stop at the aldehyde, exactly analogous, exact same thing. The one with excess Grignard to make a tertiary alcohol, exact same thing. And the Gilman reagent, exact same thing. So really the only major difference, besides some of the nuances here, obviously, the synthesis and the hydrolysis, is really, I would say, kind of these three reactions and this, that you don't need pyridine because you don't make HCl when you react an alcohol with an acid anhydride. Oh, right. There we go. Now, I told you that acetic anhydride, AC2O, is going to come up as a reagent in the class, and it does. Check this out. So remember, acetic anhydride is this molecule, so acetic anhydride, okay? And I said it can be used to acetylate, or it says here it can be used to acetylate an alcohol or an amine to make an ester or an amide. So this is our acetic anhydride. And what do we end up with? We can end up with an ester, or we can end up with an amide, an ester or an amide. And we see that shown right here. So this is nothing more than reacting acetic anhydride with an alcohol makes an ester. That's the reaction on the top. And then it says that treatment of, what did they have on the slide? I think it was a primary amine with acetic anhydride gives you an amide. Okay, so what I'm showing you here is just rehashed on this slide over here. So it's a great way to add an acetyl group onto an alcohol or an amine. Now, if you're wondering, Mr. Dion, those are on the last slide. Why are you showing it to me a second time? Well, it's because acetylation of a hydroxyl or an amine are key steps in the synthesis of aspirin and Tylenol. So I'm sure that everybody here has heard of both of these drugs, and I'm sure that some of you have even looked up the mechanism of action of aspirin, which is what we call a COX-2 inhibitor, or sorry, a COX inhibitor, so cyclooxygenase. I'm not going to get into the whole enzyme thing and the whole biochemistry of it today, and prostaglandin synthesis and all that stuff. That's something that we'll talk about at the very end of the class. We'll talk about PGs a little bit. But you take this compound here, so this is salicylic acid, salicylic acid. And what happens if you treat this alcohol with acetic anhydride, you add an acetyl group and you end up making acetyl salicylic acid. And you probably know it by its trade name, which is aspirin. If we take para-aminophenol, so this compound here, we treat it with acetic anhydride, we make acetaminophen or paracetamol, which is known by its trade name, which is Tylenol. So those are pretty cool reactions. And, you know, I mean, aspirin is a really old drug and Tylenol is old too, but these are parts of the synthesis. So now you know why acetic anhydride is so important. It's used for all kinds of cool things, naming these two drugs that I'm sure, you know, most people have, you know, probably have them in the medicine cabinet at home. I know I do. All right. So with all that information about acid anhydrides, let's turn our attention to a couple of questions. And you can see that the anhydride that we're staring at here right away, it's not acetic anhydride, is it? Right? We would call this benzoic anhydride. Okay. So what's going to happen here? We've got our anhydride. So this is our anhydride, or our acid anhydride is the proper term. And then we have phenol. So we have an alcohol. Okay, let's go back to our summary. And what's going to happen if we take an alcohol and we treat it with our anhydride, we're going to make an ester. Okay, that's all we're going to do is we're going to add part of the anhydride to the alcohol to make an ester. So let's put that together. Let's go down here. And what we're going to end up with is our phenol. So I'll just draw it like this. So this part comes from our alcohol, and then it's going to have the benzyl group attached to it. So we're going to have our carbonyl, and then we're going to have our aromatic ring coming off of here like this. Not the prettiest drawing in the world, but that's the idea. So we end up with this would be called phenylbenzoate. So this is the product, and you can practice your ester nomenclature. Phenyl benzoate. Benzoate is what you would call this guy. And then the byproduct, which isn't shown here, let's draw it in. It doesn't ask us to do this. It just wants the major product, and we've already provided the major product. But the minor product, the side product, would be benzoic acid. So that would be the byproduct is benzoic acid. And remember, this is a weak acid. And if we have a weak acid, we don't need pyridine. So no pyridine required, like that. Next one, you can guess we're going to be synthesizing an amide because we're taking our anhydride. We're treating it with this amine. Let's go back. Look at the review slide. It says if you have a secondary amine like this and you have your anhydride, what you do is you put your acyl group on the nitrogen to make a secondary amide. So let's try and draw that. Just kind of connecting the dots together here. Let's start with the amide portion. So we've got our nitrogen. It's got one R group, two R groups. The R groups are both ethyl groups, so 1, 2 carbons here, 1, 2 carbons here. Then we have our carbonyl, and that carbonyl is going to be attached to, let's get a total of 1, 2, 3 carbons. So we've got 1 already, 2, 3, like that. There we go. And should try to come up with a name for this guy. We've got NN-diethyl propionamide is what you would call this. So you could call this N-N-diethyl propionamide. That would be the common name. And the systematic name would be N-N-diethyl propanamide. Like that. Okay, there we go. So now we've covered synthesis and reactions of acid chlorides, and we've covered synthesis of acetic anhydride, then synthesis of other anhydrides, and the reactions of anhydrides. So the next section, section 20.10, deals with esters. And so I want to take a short break before we get into esters. Esters is a heavy subject, but just to put the bug in your ear before we start this section, I can tell you right now, I have many students who express to me every semester, including this semester, that they're like, hey, Mr. Dion, I'm thinking about writing an MCAT. Even if you're on the fence, I'm thinking about maybe dental school and writing a DAT exam. Well, I can tell you that if you go into my office right now and look on the floor, I have all my DAT materials because I like those. I think they're kind of interesting. And if you look in the organic chemistry section, there's always questions about esters, whether you're interested in MCAT or DAT or PCAT or any other exam that might involve organic chemistry. Now, I'm not saying that to intimidate you. I'm just giving you a heads up because a lot of my students are interested in those things. So we'll take a short break, then we're going to come back and we're going to tackle some ester chemistry.